pull up the PowerPoint here. Okay. Now, few announcements first. We're back recording, by the way, as I said. Looks like I'll be able to use this until they get mine worked on. He had thought he'd have mine ready Friday. He was nowhere close, so he pulled out this one from somewhere and said, "Yeah, I'll put the stuff on it." I can't do everything on this I could on the other one, but most of the stuff for recording I can. But I had to, that was the other thing that slowed me down too, because I had to reset this one up to take my YouTubes and stuff like that. So, the next major things that I was going to talk about were office hours. I guess that's the main one. Monday to Wednesday, my office hours stay the same, 3:15 to 5:15. Now today I'll probably be here a lot later than 5:15. I did get your test graded, but I don't have it in Blackboard yet. And I got the first class and this class graded. I've got 2 more classes to finish grading, and then I'll start putting grades in Blackboard. I had, besides the football game Saturday, one of the busiest weekends I can imagine. Yesterday afternoon we had to go to Atlanta for something, and we drove back last night, and it was after 12 before I got to bed. So if I'm sort of flakier than normal today, if you think that's possible, that may explain part of it. It's not that funny. Okay. Now.
That was funny because like yesterday I went all the way to Pensacola and back.
When? Yesterday? Well, you're young. I'm not. I'll put young and foolish, and I'm sorry, I won't say that. Okay. What's you going down there for?
My brother outside the game.
Oh, wow. How'd they do?
They won 2-1.
Excellent. That must be quite a good team to go that far.
Yeah, well, I didn't drive, that's the good thing.
Huh?
I didn't drive down there.
Yeah.
I designed.
Yeah, but I mean, he must be on a pretty good team that he's traveling that far for soccer games.
Oh, yeah.
Or matches, actually, aren't they?
Yeah, they're like, I forgot what league they are, but they're really good.
Yeah, I figured they must be. What grade is he?
He's a junior in high school.
Okay. But this is a high school.
No, this is for just travel ball, basically.
Yeah, traveling ball. Yeah, that's what I was thinking. I have a godson whose parents are from Germany. He's really good, but he's only like in the 7th grade, I think. But he's on a traveling team too, but certainly not that one. Good deal. And baseball team's getting ready, right? Good deal. Okay. We're going to do example 1. They don't have a slide for it, so I was going to use this slide. Oh, I was finishing my office hours. Monday, Wednesday, 3:15 to 5:15. And I hope to get things at Blackboard. Number 2, my Tuesday, Thursday schedule has now changed. First mini-term, my physical science class started at 1:15, so that meant I had from 12:15 to 1:15 was the only office hours I had on Tuesday, Thursday, which is also my lunch hour, but that's when I was in the office. Starting tomorrow, my second mini-term class doesn't start until 3:15 because some of the automotive students are in it, and they're in their classes. They're on a block schedule, mini-terms only, and they go until 3, so they can't get over here until 3:15. So that means I have office hours on Tuesday and Thursday from 1:15 to 3:15, but then the downside of that is I'm here till 8 o'clock at night rather than 6 o'clock at night, which I was the first mini-term. So it's cost, okay, but I've got office hours finally. Okay, Fridays are still the same, 7:45 to 11:45. So I'm usually later than that. All right, let's set up. Takes all these things to set up first. Okay. Here's example 1. Evaluate this. The integral of 1 over the square root of 1 minus x squared. Did we not start this problem last time we made? No, I don't remember. We didn't?
I just have it written down. We were about to start it.
Okay. Was this the one I started and you started giving me suggestions of how to begin? I think that might have been it. And y'all were going to try a substitution, or you were going to write it as 1 minus x squared to the negative 1/2 power.
Yeah.
And some other things like that worked really well, didn't they? I didn't. Okay, that's how I remembered it too. Okay. What did we decide to do rather than that? A trig substitution. Since the title of this section is trigonometric substitutions, it sounds like a great thing to do. What might be that trig substitution? How do we do that? X. This is different from our other substitutions because there we introduce a new variable, u, to be some form of x. This time we're letting x represent what? Say again? Okay. Yeah. In this case, the a is 1, so we can't just do sine theta. Okay, then what next? There's several next you can go to. Which one you want to do first? Next. X squared. Then x squared. Well, let's just continue here then. X squared is equal to sine squared theta, right? And that leads to what you want to do next. One minus x squared, right? That shows up here, right? And what's 1 minus x squared then? It's pretty easy. Just put a 1 minus in front of x squared. It's a long trip from Pensacola, wasn't it? 1 minus sine squared theta, right? All we're doing is trying to get this to get in terms of theta. If you want x equals sine theta, then you got x squared here, so x squared would be sine squared theta. 1 minus x squared would be 1 minus sine squared theta. And what is 1 minus sine squared theta? Cosine squared theta. So this is equal to cosine squared theta. And then we put it under a radical, and the square root of cosine squared theta would then be cosine theta. All right, so our square root of 1 minus x squared, which in your denominator there, is going to be a cosine theta, right? So those are all consequences of choosing x equals sine theta. Now what we'll do, what's your next step here? Then what? If x is sine theta, what other part? We've taken care of all this, but we haven't taken care of this. What would that be? Let x equal this, then next step. We always did it. Let u equal something, then dx. Y'all were trying to avoid this, weren't you? What's that?
It doesn't show where your cursor is, so I didn't know what you were talking about.
Oh, you don't see the mark under here? You see? Yeah, I don't have a hand, so I have to mark it. Maybe a neon lights. Would that work? Okay. All right.
So would the x be using cosine or using sine?
What was that? What was x?
Oh, it was sine. So
Yeah.
it would be negative cosine.
That's why you're avoiding that answer, wasn't it? I knew there was an ulterior motive here. It's what? Oh, yes, cosine theta. You're no longer. X's were over here. Over here we're in. Nope. I don't see any U's on there. What's your new variable? Theta. D theta. Right? Okay. So let's see what we've got then. We've got the integral of 1 over, and what is the square root of 1 minus x squared? It's 1 minus x squared, square root of 1 minus x squared. That becomes cosine theta, right? That's what we did all the way across there to get to cosine theta. And then your dx is what? Cosine theta d theta. So guess what? That integral is now. D theta is all. And what's the antiderivative of d theta? Theta. All right, now all we've got to do is go back and get theta in terms of x. So how do we do that? So here's another consequence of this. If x is equal to sine theta, what would theta be? Say again? Okay, multiple choice here, right? Okay, how do you undo something? They're not integrating, yeah. Undo derivatives, antiderivative. Undo a function, you do a. I think we got some antimatter in here somewhere. Okay. Okay. Maybe we need some anti-thought. No, we won't go there. Okay. And let me just make a little hint here. I don't know if this will be a useful hint or not. What value x do you happen to be stuck with here? Huh? No. Value of x up there. The original thing.
Root 1.
Yeah, something from -1 to 1. Oh, you can't even have -1 or 1, can you? Because then you'd have a 0 in the denominator. So anything between -1 and 1. Okay, if x can only be between -1 and 1, and x is equal to sine theta, what could theta be? What do you put in for theta to give you a -1 here? Sine of what gives you a -1? I want to know what button you're going to push.
It's
I want to know what button you're going to push.
So we said what sine equals -1?
Yes.
It would be 3 pi over 2.
Okay, that's 1. Go backwards.
Pi.
Not further back than that.
Pi over 2.
Pi over 2 is 1. Pi over 0, by the way. You need another -1 back this way. What button did you push, or did you push one?
Pushing all of them.
Yeah, okay. None of them pops out.
It's not 3 pi over 2?
Huh?
It's not 3 pi over 2?
3 pi over 2 is a correct answer, but there, okay.
Negative pi over 2?
Negative pi over 2. Okay? So, how did you get that? I know, but think of what you just did there.
Instead of going clockwise, no, counterclockwise.
Okay, yeah, I know all that. Okay, but what did you do going from 1, if you're taking the sign of something, and you go from 1, from pi halves, or negative pi halves to minus 1, that's taking the sign of it. What did you do to get from a minus 1 to get to theta equal that? Hold your calculator. Where's your sine function? Let's write it above. What is that thing called? Huh? Yes, it is. That's one name for it. Arc sine or inverse sine. The minus 1 usually is right inverse. And you're in agreement there, right? Yeah. Okay? So that's what you do. If x is equal to sine theta, theta is equal to inverse sine of x. And that's exactly what you put on the calculator, right? The inverse. Huh? Okay. So theta is equal to inverse sine of x, or arc sine. Okay? Here's how that's right, I didn't teach y'all inverse trig functions. That was back in trig, wasn't it? Okay. When you have an addition problem, you're undoing that. Subtraction is the inverse of addition. Multiplication is the inverse of division. Division is the inverse of multiplication. Square root's the inverse of a square. The square is the inverse of the other. They're inverse function. One undoes the other. Now, why we don't use 3/2 pi? Because if you draw the sine function, if you started at 0 and went to 3/2 pi, can you take the inverse of that function? Because you failed the horizontal line test. Does this ring a bell somewhere there? Remember, to be a function, it has to pass the vertical line test. To do an inverse of it, it has to be a 1-to-1 function. A 1-to-1 function means it's either strictly increasing or strictly decreasing. So we've chosen, the powers that be chose for sine, because sine is a periodic function. It can't possibly be 1-to-1 everywhere. So you choose a segment of it where it is 1-to-1. And so sine goes from -1 to +1 between negative pi halves and pi halves. That's the portion that we use. And that's the only portion we use. Okay? Now, if we had used 3/2 pi, which is over here, you would have had to start at pi halves and go down to 3/2 pi. That's sort of an awkward segment to use. You could have, but they've defined it. No, let's go from negative pi halves to pi halves. Cosine goes, on the other hand, from 0 to pi, because cosine starts up here at +1 and goes down to -1, and you have to be one period. I mean, not even a period. One segment that doesn't reverse itself. So that's what we did. We took an inverse sine of x. And what else did we have to do? What kind of integral was it? Second? I can't hear. I see lips moving, but I can't make out sound. It's your favorite last step. Plus C, okay. Plus C here or plus C here. I don't care where you put it. Okay. So it's inverse sine of x plus C. All right. That was so much fun. Let's do example 2 and make a rhyme every time. We'll do the integral of the square root of 1 minus x squared dx. How would you go on this one? Same thing. And what was that same thing? Let x equal sine theta. Good start. Now, which way you want to go? This way or this way? Got to do them both at some point. I don't care. Dx, okay. Then dx is equal to? Almost. D theta, very good. Okay. Now let's deal with the integrand. You got that part done. Check. Let's do that part. And you don't have to do all the steps. Well, you do have to do them all, but you don't have to string them out. You can do them as concisely or expandedly as you want. You don't. Yeah. Okay, x squared would be sine squared theta. Okay, we don't just have an x squared. What do we have? Okay, a 1 minus. So 1 minus x squared would be 1 minus sine squared theta. Okay, but you don't just have a 1 minus sine squared theta, you have a, huh? Okay, you have a square root involved in that too. So we can put a square root on it. So this thing would be that thing, right? But what is 1 minus sine squared theta? That's not, okay. Square theta, and then take a square root of it, and that produces cosine theta. All right, I think we're ready to do our integral now. What's the square root of 1 minus x squared when you do your trig substitution? This thing became that, right? So that's the cosine theta. And what do dx become? Cosine theta d theta. Now, this becomes the integral of cosine squared theta d theta. Now you have at least two possibilities here. What might you do? I'm happy with either one. There may be more than two, but I can think of two off the top of my head.
When there's d theta afterwards, I mean, you gotta take the derivative.
Yeah, you do an antiderivative to get what's that. This is the integral. Is that what you're asking? I didn't understand the question.
Yeah, like, so when it's cosine or anything, and there's like a dx, or right as it appears, d theta, that means you take the antiderivative, right?
Cosine squared theta.
Yeah.
Right. That's what I'm asking. How do you do it?
Just do it.
Huh?
You do cosine cubed over 3 theta.
Yeah, but then you would have a chain rule thing there, wouldn't you? Ooh, where's he looking? Yes, that's one option, isn't it? Go to a table. Okay? The other option was figure it out, and that's not hard either. But what did you get off your table? Theta over 2 plus sine what? Sine squared theta? Oh, sine cubed? 2. Oh, sine of 2 theta, got it. I'm sorry, I can't hear. Over 4 plus c. Okay. Now, that may be a little bit of a difficult form to use. because of that sine 2 theta. Huh?
It gives 2.
Okay, what's the other one?
Theta over 2 plus 1/2 times
Sine theta, cosine theta? Plus C. My pen is very slow right now. Okay. That one I think will be a little easier to do. Number one, we already know what sine theta is. Right? That's your x. But I think you're going to have to do a little drawing here to get what cosine theta is. So let's do a little angle here and call that theta. And sine theta is x over, which is sine theta is x over 1, right? So the hypotenuse would be 1. If this is your right angle, there's your angle theta. Sine theta would be x over 1, right? Opposite over hypotenuse. Some old hen. Because if sine theta is equal to x from here, that was your assumption, I need that as a ratio. Well, x is x over something, what would it be over? So that makes this the opposite side, this your hypotenuse. Okay? Can you tell me what this is? Actually, we have it right here. Cosine theta is square root of 1 minus x squared. See, what we're doing now, this is a correct answer for theta. What we need to get it is back in x, because the problem came in x is we made the trig substitution to give you thetas, but here this tells you what x is. Okay, sine theta is x, cosine theta is that. So we didn't need this, but I was going, you could get it that way. So let's rewrite it. Oh, and what is theta? We need that too. How can you get what theta is? Second? Ah, very good. Theta is equal to what? Sine, yeah, inverse sine of x. So now you got that in terms of x as well. So this would be 1/2 the inverse sine of x plus 1/2 x, that's what sine theta is, times the square root of 1 minus x squared plus c. There's your answer. All right. Let's see how the book did. 1/2 inverse sine of x plus 1/2 x times 1 square root of 1 minus x squared plus c. Good for them. They got it right. You see how that works? Okay. Now they did the triangle too. I just wanted to show you this works out this way too. I just happened to notice we'd already done it, so we didn't have to do it in this problem. Some problems you will not have that up there. So here's what you would do. If this is x and this is 1, you want to give that a name? You can't do cosine for this, right? Because cosine is adjacent over hypotenuse. But we don't know what adjacent is. How do you get cosine now? The adjacent side. Say again? You want to give it a name? Okay, what if this is b? Now, can you give me a relationship here between 1x and b?
B squared plus x squared equals 1.
I like it, okay? B squared plus x squared is equal to 1. But now I want b in terms of x. So what would we do? Say again? Yes, subtract x squared from both sides. And that gives us b squared is equal to 1 minus x squared. And then take the square root. So b is equal to the square root of 1 minus x squared, which is exactly what we got up there. And then we have cosine theta is equal to b to 1. Square root of 1 minus x squared. In other words, it's square root of 1 minus x squared. Which we already had in this case, but this is how you get it otherwise. Now, the only thing there is you have to make sure that your is not plus or minus b. But we're just going to deal with the positive for now. We'll put it over here in the first quadrant, which makes b positive. All right. Now, the only sort of difference between the first problem and this one is this one does allow you to have x equal plus or minus 1. In the previous problem, when that was in a denominator, it couldn't be. Because now it's okay for this to be 0. Okay? But it's not okay for x to be less than minus 1 or greater than plus 1, because then you have a negative in the radical, and that's not allowed. Okay? But you are allowed to have 0 in the radical. So that's okay. The previous problem, the thetas could only go from minus pi halves to pi halves, not including the influence. This one can be minus pi halves to pi halves, including the influence. Or in other words, 1 to 1 for x. Okay. So, any questions on that? And the book got it right. Good for them. Next thing we're going to do is this. Integrals involving, this system is really, really slow. Of course, I'm pretty slow myself. Okay. The square root of a squared minus x squared. Okay. Not a lot of difference here from what we were just doing, except that now it's not x equals sine theta, it's x equals a sine theta. Okay? And we'll see how that pans out. If you have that in an integral, okay, if x squared of a squared minus x squared occurs in an integral, anywhere in the integral, as long as a is greater than 0, okay? So you could have a negative 3 squared, okay? You want it to be a 3 squared, okay, or whatever. It would be 9. Negative 3 squared would still be 9, but you could, then your substitution wouldn't be right. You need a to be positive, okay? You try this substitution, x equals a sine theta, okay? Now, they showed you the dx here. Did they get it right? Yeah. Dx is a cosine theta. Now, they just magically wrote that on the board. Let's see how they got it. Well, first thing, they want, I blew it up, so I have to reduce it now. There we go. I don't know why it didn't work the first time. Okay. There it is. Okay, I couldn't find my pen. If x is a sine theta, but you have a x squared here, you do x squared, but it would be equal to what? If x equals a sine theta, X squared would be a squared sine squared theta. Okay? But you don't just have a x squared, you have a squared minus x squared. So a squared minus x squared would be what? A squared minus a squared sine squared theta. But what can you do with that? You have a common factor of a squared, so factor that out. It'd be a squared times 1 minus, second, sine squared theta, okay? And that would be a squared times cosine squared theta, okay? But you didn't just have an a squared minus sine squared theta, you had the square root of that. So the square root of this would then be the square root of this, which is the square root of that, which is a cosine theta, which is exactly what they got there. Right? Okay. So everything they wrote there was correct. All right. And that's what we'll use when we do our thing. We'll also draw little pictures. Okay? This time, when you draw your triangles, if you make if you make your little angle here, theta, what is that? If x is equal to a sine theta, how would you label what you got? X equal a sine theta. Let's isolate the sine theta, and what does that give you? Say again? X over a would be sine theta, right? And if that's theta, where's your x, where's your a? Opposite. A is hypotenuse. Guess what this would be down here? A squared minus x squared, the square root of that, right? Kind of like what we just did. Buy it? Okay. So, keep all those kinds of things in mind. Okay? So let's do example 2. Okay. This is the figure, by the way. This is aggravating. The cursor doesn't work here, so. No, that's not what I want to do. That's what I want to do. Zoom in. Okay. Oh, no, that is the one for example 2. Okay, so let's back out of this. So this is example 2. Integrand involving a squared minus x squared to the 3/2 power. Okay? This is example 3. Isn't it? Top of the next page. Is that what you got? Yeah. Yeah, that involves that. So here's your integral, x squared. I'm going to go ahead and put the dx up there. I like it up there with it, okay? Over 4 minus x squared to the 3/2 power. Okay. So basically you have a form that has at least it looks like it's got what close to what we have. Now, if that had been an x, what do you do? Substitute. What would be your substitute there? Yeah, as in u. minus 2. Yeah. But we don't have that. We have x squared. Oh man, a big this here. I can't think of any way to manipulate that. So when that doesn't work, and you have got something to the 1/2 power here, let's go into that part. So let's do our trig substitution. What would that be in this case? Let x, for trig substitution, let x equal what? See that block? Well, let me just go back a block. Right here, what we had here was 4 minus x squared, wasn't it? It was the integral 4 minus x squared, right? Right? And with 4 minus x squared, that's a is a 4 is what squared? 2 squared. 2b positive. So then your substitution would be x. The substitution would be x equal 8. So x equal 2 sine theta. Right? Alright. Now we can go either to the right or below. I don't care which one you want to do. Either imply here or then here. You tell me. Choose one. Wave off a sign. Okay, what? Okay. If that's how he communicates with his catcher, he's in serious problems here.
So would it be dx equals?
Okay, let's do dx. See, he shows us that one. Okay, dx equal what? 2 cosine theta. D theta, all right. X squared. What was x squared be?
2 squared sine squared theta.
That would be like 4 sine squared theta. Okay. Say this again now. You know, for part of this, we're perfectly happy. We have x squared up here. There's my x squared. We're happy with this. We're going to hang on to that. We're not going to erase it. We're not going to skip it. We're going to hang on to that. We got our dx. We got this. The part we don't have quite is 4 minus x squared to the 3/2 power. So let's get that. What do we have to do to get that part? 4 minus x squared is what? 4 minus 4 times sine squared theta. Is that what you said? Okay, and that would be second. Yeah, take the square root of this and the square root of that. And what would that be? 2. Take that all the way out. Factor out a 4. Take the square root of 4 is 2. Okay, got that. Okay. You factored out a 2 out of both of those, right?
Oh, so would it be 1 minus
The square root of 1 minus sine squared theta. Okay, I'll buy that. Are y'all with me? No magic? all legal, right?
Where the square root come from?
What's that?
Where the square root come from?
The square root, it came from the problem. Well, we're getting to it, okay? What this means here is the square root of this cubed, right? So that's where the square root came from.
Okay, so we're just splitting it up.
Huh?
Just splitting it up.
Yeah, I'm splitting it up. So just like I did this, I chose an x, and then I did an x squared, then I did a 4 minus x squared, and then I'm doing the 1/2 first, and then we'll do the cubed. Now, you don't have to do it this simply if you don't want to. I'm just trying to get you to see where this is coming from. After a while, when you get used to it, yeah, I can skip 2 or 3 of these steps. Yeah, that'll be fine as long as it's legal and you do it right. Okay. So, yeah, but that was a good question. Where the square root came from that 1/2 up there. So what does that give you?
2 cosine.
Yes, this is 2 cosine theta. Okay? Now that is your denominator. No, that is with the square root in there. And what you're doing with that is cubing it. Then this thing cubed is that thing cubed is this thing cubed is this thing cubed, and that would be what?
That's the square root of cosine theta.
Say again?
Does the square root go away? The last
Right here?
Yeah, the next step.
The next step. Okay, I thought you told me to do cosine theta.
Is the square root of cosine theta?
Okay, it's the square root of what's 1 minus sine squared theta. Okay, I just did what you tell me to. Yeah, so don't tell me wrong. Okay, is that right now? Now we're going to cube that, and what does that give you? Eight cosine cubed theta. Okay? Now, let's look at our pieces. This is that, this is that, and this thing here is that. Right? So let's put them all together and see what we get. All right? It's the integral of, what's your x squared?
8 cosine.
Second,
Would it be 8 cosine theta?
x squared. 4 sine squared theta. Right? Now we don't quite have our d theta. We're close, but no. Our dx. So we got exactly our dx. Okay, and what's our dx? 2 cosine theta d theta. Okay? And what's our denominator then? 8 cosine cubed theta. All right. Now, 4 times 2 is 8, so the numbers go away, right? And then what we've got down here is a cosine theta here and a cosine cubed theta here. So that's going to wipe out the cube and make it a square, isn't it? Boy, that's an ugly 2. All right, let's try that again. Wipes out the cube and makes it a square. You buy that? Okay. Now, second, you could make that a tangent square. That probably is a very good idea. That's the integral of tangent squared theta d theta. And what will that give you? Come on, trig. Oh no, you might need that. Integral of tangent squared. He's going back a couple pages to his favorite page back there.
Tangent over it could be tangent 2 minus 1, or should be just tangent theta.
Okay, a little louder, I can't hear.
Tangent theta minus the integral of whatever. I don't know, I'm confused.
That's what I can't hear.
Confused.
Huh?
I don't know.
That'll be a 1.
Yeah, just be 1 dx is the integral of dx. Or d theta.
It would be theta d theta.
Say again?
Oh, wait, no. Yeah, it would just equal d theta.
Is that right?
Yeah.
You agree?
Yeah.
That's easy to say, isn't it? Yeah, okay. All right. So what's the integral of d theta? Minus theta plus c. Okay? Now, I have such a little space here. It looks big there, but I have a little space here, and that's what makes my writing look too big there. So what we need to do, here's our little triangle that I was going to draw, but they've already drawn it for you. Here's your theta from this. X equals 2 sine theta, solve for theta, sine theta, and that gives you x over 2 is equal to sine theta. So if this is theta, there's your x, there's your 2, right? That makes this the square root of x squared minus this squared, right? Square root of 4 minus x squared. Now we've got a tan theta. What is tan theta? Opposites and adjacents and hypotenuses. Opposite of adjacent. So what would that be in this case?
X over 4 minus x squared.
The square root of 4 minus x squared. Okay? So, our solution here is, I think I'll write it up here. That would be x over the square root of 4, I can't write, 4 minus x squared minus theta. Well, let's go here to get your theta, right? X over 2 is equal to sine theta. This pen is so strange. And then what do we do? Say again? Yeah, the arc or inverse, either is fine. So what would I write? Theta is equal to arc sine of x over 2. Right? So minus arc sine of x over 2. And then we put our plus c. Okay, let's see how they did. I'm on the wrong page. There we are, example 3. X over the square root of 4 minus x squared minus inverse sine or arc sine of x over 2 plus c. Yes. See how we got there? Okay. Good deal. Now, the next substitution, or the next type of integral we do is this one. Integrals involving 1 minus x squared, or a squared minus x squared, but square root of x squared plus a squared, which you could have written as square root of a squared plus x squared. It doesn't matter which order, because this is addition. Addition is commuted. Subtraction is not. You had to put a squared minus x squared. So this one could either be a squared plus x squared or x squared plus a squared. It doesn't matter. If that's your integral, if your integral contains a radical with a plus between your variable squared and something else, that occurs, and we're always going to assume a is positive now. Try this substitution. X equal a tangent theta. Now where did they get tangent theta? Because tangent squared, 1 plus tangent squared theta, or tangent squared theta plus 1 is going to equal secant squared theta. So that's where that's going to come from. So there's your x equal a tangent theta. What else would we need to do to that? We're going to have to shrink it to do it. Why does it do that? Yeah, okay. X equal a tangent theta, what follows from there? Okay, x squared would be a squared tangent squared theta. Okay, and what would follow from that? Atom. So, adamant, okay. X squared plus a squared would be a squared tangent squared theta plus a squared, right? And then you can either take a square root now or figure out what that is now. I don't care what you want to do next. Factor out the a. So that would be a squared times tangent squared theta plus 1, right? And what would that be? A squared. Oh, you want to take a square root of it now? That'll be fine. We'll take a square root of this. That'll be a square root, well, all right. The square root of a squared would be a, and then that would be the square root of tangent squared theta plus 1. And what is tangent squared theta plus 1? Secant squared theta. Square root of that would be secant theta. Okay? So all this thing would then be secant theta, or a secant theta. But that's exactly what they got here. You see, that's how they got it. Now what we hadn't done yet was dx. And what would dx be? If x is a tangent theta, what is dx? X is a tangent theta, what's dx? Anyone remember?
If a is tangent theta,
Right.
dx would be secant theta.
Yep.
A secant theta.
A is correct. But secant theta means something else.
Secant theta, tangent theta.
That's derivative of secant theta tangent theta. So what's the derivative of tangent theta?
Secant theta.
Huh?
Secant squared theta.
Secant squared theta. Secant a secant squared theta d theta. Okay? So now we've got all the pieces we need. Okay? The substitution is x equal a tangent theta. Expand that and you get the radical x squared plus a squared will be a secant theta. Your dx will be a secant squared theta d theta. So we'll move from that to example 4. Now let's see if example 4 think they've got it, the figure for it, but they don't have the problem for it. So let's write it down. Yeah, okay. The integral of 1 over the square root of x squared plus 9 dx. Okay. Now, if there had been an x in that numerator, what do you do? Substitution. Don't worry about trig substitution. We don't have an x up there. Okay? So it looks like we're stuck with we have the opportunity for a trig substitution. And what will it be in this case? Say again? I can't hear. Let. Okay, got it. X. Oh boy, we're on a roll now. I got the equal sign. You don't have to supply that. I did the hard part. Okay, getting really upset there. Okay. Say again? No. Tangent. That part is right. Okay, tangent theta is better. Missing something. We got the x. A. Oh, what's your A here? Yeah, we do. 3. Right? That was your A squared. The 9 was A squared, so the A has to be 3. All right, which way you want to go on this? To the right? Okay, what would you do next? Okay, x squared would be 9. Tangent squared theta. Okay. Where do you want to go with that? Don't we need second? Plus 9. So we'll do x squared plus 9, and that will be 9 tangent squared theta plus 9. Where do we want to go with that? Factor out of 9. Tangent squared theta plus 1. What's tangent squared theta plus 1? Secant squared theta, so this would be 9 secant squared theta. Got it? Now, that's as far as we can take our x squared plus 9, but what was it in the problem? It was a square root of x squared plus 9. So we'll do a square root of that, and a square root of that, and a square root of that. And when we do a square root of that last one, which is the same as the previous ones, what does that give us? 3. Secant theta. Okay, got it. Okay, let's go to the below part here. What's our then? Dx is equal to 3 secant squared theta d theta. All right. I think we got all the pieces we need. Let's rewrite our integral in terms of thetas. Now, we had it in terms of x's. Let's do it in terms of theta. In the numerator, we had a 1 dx, so let's just put dx will be 3 secant squared theta d theta, right? Over, and that whole denominator was wound up being 3 secant theta, d theta, right? Oh, disagree, huh? There's your denominator. Okay, square root of x squared plus 9, right? Thought you led me down the primrose path here. Got to that. So instead of that, we put that. Right? Oh, without the d theta. Where'd you get the d theta from, huh? Where? You're confusing me. Okay? I just got carried away with d thetas. Okay? Then what happens here? 3's go out. One of the secant thetas go out. And we have the the integral of secant theta d theta. That d theta belongs there. Does anyone remember what that is? If not, you can find it. I knew he was going. He's going to have that page dog-eared. Log of secant theta plus tangent theta plus c. Okay. Now I put absolute values there. Frankly, we're going to stay in the first quadrant, so we will be able to remove those, but I bet you they had those in the problem. But we got to figure out what in the world secant theta is. Now, from this first substitution right here, x equals 3 tangent theta. That's where we started, right? Well, let's get that in terms of tangent theta. What's that? Okay, wait. Divide by 3, right? So x over 3 is equal to tangent theta, right? Draw your triangle. There's your theta. Whoa. That's not our picture. Where does that picture come from? That must have been the previous edition. So forget that. It's the triangle is fine. It's x over 3, right? No. It's tangent theta. So that's x over. That would be it's a 3 down there, and this will be what? 9? What's that? Okay, x squared plus 9, square root of that, right? So this will be the square root of x squared plus 9. Ooh, where have I seen that before? Oh, that's our denominator, isn't it? Yay, okay? So, we're going to get there, hang on. Okay, so now we know what, you know what? We really didn't need it, did we? We had everything we needed without the picture. Because this is the log of, I'm going to put the absolute value still there. What was secant theta? Secant theta here was right here. Secant theta was the square root of x squared plus 9 divided by 3. So it's the square root of x squared plus 9 divided by 3. Without our picture. Okay. With the picture, it's hypotenuse of the adjacent. The square root of x squared plus 9, that's a 9, over 3. So that's what your secant theta is. Tangent theta we had from the beginning, that's plus x over 3, right? Plus c. Okay. So this is the log of I'm going to write it this way. X plus the square root of x squared plus 9 over 3 plus c. You can put the absolute values, but that 3 is not part of your answer there. Okay, x plus. Okay, let's see how the book did. Oh, they can do one more step. I forgot this one. Where will I write it? This will be the same. Remember our rules for logarithms? The log of x plus the square root of x squared plus 9 minus log 3, right? Plus c. Because rules for logarithms, it's whatever if you got a quotient, the log of the numerator minus the log of the denominator. Log 3 is just a constant. Let's pile that in with the other constant, so you just have this thing plus a constant. Okay? So your final answer is the log of x plus the square root of x squared plus 9. And as long as x is, it doesn't matter what x is. If x is positive, this thing's certainly positive, right? But even if x were negative, give me a negative value for x. Any negative value for x. Negative 5. 5 squared would be, negative 5 squared would be, positive 25 plus 9 would be 34. Square root of 34 minus 5. Still positive. Because 5 is square root of 25. So yeah, no matter what value x you put in there, you get a positive number. So you don't need the absolute value bars anymore. But then you do need a plus c. Maybe not the same c you had before, but some c. So this is example 4. Where was our final answer? The log, they kept the absolute values in there. It's okay. Nothing wrong with it. Square root of x squared plus 9 plus x plus c. Now, you might wonder why I reversed the order of those. And it's just my preference. Because with my sort of sloppy writing, which you probably won't believe I have sloppy writing, it's not that funny, okay? If you wrote this first plus x, if I got a little carried away with my radical symbol there, and I covered part of the plus, you might wonder if the x was in there or not in there. If you write the x front, there's no way of guessing that it might be under the radical. It's obviously not. So that's why I wrote it that way. But you don't have to. It's not required. Huh?
This might be a dumb question, but where does the log of 3 go?
Because it's just a constant. So add it to the other constant, and that's just a constant. So you incorporate it in the constant, basically, is what you do. If you wrote it down, you're not going to lose any points for it, you know. But you have that. The cleanest thing is to incorporate it in the constant. If that had an x in it or any other variable in it, you can't do that. But if it's just a number, yeah, you can do that. Okay. Now, our last form is this form. Okay. Integrals involving an x squared minus a squared. So notice what we've had. Square root of a squared minus x squared. Yeah, we can deal with that. X squared plus a squared. Yeah, we can deal with that. Now x squared minus a squared. Not going to be a sine, not going to be a tangent. But if you think back of your tangent Pythagorean theorem, if secant squared is tangent squared plus 1, right? we used that last time. Then tangent squared would be secant squared minus 1, x squared minus a squared. So in this case, we'll let the x equal a secant theta. Okay? That will be your attempt. Okay? And they show you your dx, which you were trying to give me before for tangent. Derivative of secant is derivative of a secant theta would be a secant theta tangent theta d theta. Okay? We got that. If we did our maneuvering on this, x squared would be, would it help to write it down? No. Okay. A squared secant squared theta, right? Then subtracting a squared from it, a squared secant squared theta minus a squared. Factor out the a squared times secant squared minus 1. It would be a squared minus tangent squared, right? Tangent squared theta, however you want to say that. And then take the square root of it, you get a tangent theta. Right? All right. So that will be the procedure we follow. Let's do an example with it. All right. I think this is example 5. Man, when it's cool outside, the air conditioner works really well, doesn't it? Old buildings. Okay. I think it's example 5, isn't it? Evaluate this. Integral of dx over x squared times the square root of 4x squared minus 36. Oh my word. I read it right? I think so. I don't think there's any way in the world a substitution, a regular substitution, will help you on this one, because you got in the denominator something inside a radical, but also something else. Nothing up there with the dx in the numerator, so yeah, this doesn't look pretty, doesn't it? But focus on the radical form, and that is a form of, that's not quite an x squared minus a squared, because you've got a 4 in front. That's kind of a big boo hiss, isn't it? So what might we want to do? Sounds like a grand idea. So let's just take this, say that square root of 4x squared minus 36. Factor out a 4, that's the square root of 4 times x squared minus 36. No, minus what? Minus 9. Okay, that's better. Why did you say 36? Okay, now, what can you do with that? So that the square root of 4 times the square root of x squared minus 9. And what's the square root of 4? 2. All right. So you could rewrite that as the integral of dx over x squared, and without doing anything else, pull out the 2, pull it outside the integral completely out there, and that will be, the square root of x squared minus 9. Now, that's all legal, right? So if you put this back in here, and then square it, put it back in there, and you wind up exactly what you had. So that's what you do to get rid of the a, this 4 here. Divide it out inside there, and pull it out of the radical and Okay? Hunky-dory with that. So, can I erase my scratch work here? Because I need the room. You're okay with it though, right? Okay. All right. Now what? What's that? Where do we go from here? We got rid of the 4, which was bugging us, so we could get it in a form that we wanted. But what do we do with that form now? And which is it? Three. Secant x. I'm kind of liking that, except I don't like x. Theta. Right? And which way you want to go, down or across? Across. Okay. What's going to come out of that? X squared is going to be what? 9 secant squared theta. And guess what, team? There's an x squared. Later we're going to substitute that right there in for that, right? But we're going to proceed because we've got more to do. What do we want to do next? Subtract 9, yeah. X squared minus 9 is going to be 9 secant squared theta minus 9, all right? And then what we're going to do with that? Factor out a 9, and that will be 9 times secant squared theta minus 1, right? Which is, what are we going to do with that? That's tangent squared, so it's going to be 9 tangent squared theta. And what are we going to do with that? Take a square root of it, because we had a square root of this, which is going to be a square root of that, which is a square root of that, which is a square root of this, which is what? 3 tangent theta. So that's what that radical x squared minus 9 is going to be 3 tangent theta. So let's go back to our integral, which is a 1/2 the integral. Whoa, we haven't done a dx. Let's do that. Dx is equal to what? 3, I got that. Secant theta tangent theta. One more little piece. D theta. Okay? So, our dx is what we just wrote down, 3 secant theta tangent theta d theta divided by, first the x squared, which is, help me, 9 secant squared theta. And what was our square root thing? Second? 3 tangent theta. Okay, I think I got it all accounted for, don't I? Well, I happen to see a 3 here and a 3 there. I'm going to get rid of them, right? I happen to see a tangent theta here and a tangent theta there. I'm going to get rid of that. Or am I? Yeah, I think I got it. So what do we got? 1/2 the integral of, okay, let's just go and do this. Let's get rid of one of these and that one. I'm not sure I really want to, but let's do it. And the 9, let's pull out here with the 2 and make it 1 over 18. And that's just going to be a d theta over secant theta. Right? But what is 1 over secant theta? Cotangent theta? Huh? Say again? Cosine. Okay, yeah. Cosine theta, integral of cosine theta d theta. Oh my goodness, I think maybe we can do that, can't we? No, now that I think about it, I'm not too sure. What's that going to be? I was kidding. Everything came to a grinding halt. Antiderivative of cosine theta.
Oh, negative sine theta.
Want to try another guess? Sine theta! All right. Derivative of sine is cosine. Antiderivative of cosine would be sine, right? Yeah. All right. Plus C, okay. All right, how in the world did we get from a trig substitution of x equal 3 secant theta to be a sine theta? Well, who cares? Well, we care. But let's go back to this original step right here, and let's figure out what is, okay? Let's draw us a little triangle, with this being our theta, and divide by 3. Secant theta is x over 3. Well, tell me what in the world the secant theta is in terms of opposites, adjacents, and hypotenuses. Hypotenuse over adjacent. So that would mean this would be our x, and this would be our 3, wouldn't it? If secant theta is x over 3. By that? Yes? You okay with it? Okay. Sounds so convincing there. All right. To get a sine theta out of that, what are we going to need to do? We need the opposite side. Well, what in the world is that opposite side?
We wrote the triangle, right?
We got the triangle, yeah.
We're looking at the opposite side.
Yeah, we're looking for the opposite side. There it is.
Okay. So it would be
Square root of
3 minus x squared.
I think not. It's always
1.
okay. The hypotenuse squared minus the other side squared, right? That would be x squared minus 9. Right? Which is basically what that part is right there. Most of the time it turns out that. So now that we know that, what is your sine of that angle theta? The square root of x squared minus 9 over x plus c. Right? Let's see what they got. Okay. They wrote the 18 with the x, which is fine. they find the weirdest way to write these. And if you can imagine trying to match up something like WebAssign with this, and they want you to guess exactly which form they count the right answer of. If I wrote this, they'd say wrong answer, and it's the right answer. It's just not written the way they did. They wrote the square root of x squared minus 9 over 18x plus c. Good deal. We have run, unfortunately, out of time. So we'll start next time with the square root of general quadratic functions. That will be bottom of page 389. Homework exercises here will be number 1, or make it 1 or 3. Sorry, 1 or 3, or both if you choose. Any of the odds 5 through 9. 11 or 13, or both. Any of the odds 15 to 31. You can try 33 and or 35. And we'll stop there and pick up the rest of them next time. Is that okay? All right. Good deal.
I have my essay written.
Oh, good.
Do you want me to send you through email, or you want me to go to the library and print it out for you?
Whichever way you prefer. Here's what I tell students when they ask that. If I get it by email, I grade what comes in when I print it on my computer. Now, if you think you have it in a great form, it looks okay on your screen, and you send it to me, whatever I print out, that's what I'm going to grade. I've kind of encouraged people to print it out and make sure it looks like the way you wanted it to, because I'm going to grade what you send me. Okay, so you choose whichever you want to do.
I'll just print it out.
Okay. See you then. All right. That would be superb. Oh, goodness. One, by the way, I don't know if you want it. There's your Calculus 1, Test 2. I didn't realize I still had that until I was just thumbing through here. I don't know if you want it or not, but okay. Otherwise, I was going to trash it. Wait a second. Good thing on all of them, but you made a lot of really dumb mistakes. So, just use the points here, just about everywhere. So, it's easy to bring up on the new calculus test board. But I'm not going to bother be any, but I would have to put that one in the midterm unless I get a paper this week. Is that possible? Okay. But if you don't, I can make this not put in a D in the midterm. I know you're going to do better, aren't you?
I'm not good. It's pretty good.
Well, yeah, I went through, I was not in places where I could do it. I don't think you drew a picture here. Did you?
I was using a graphing calculator,
Something must have done wrong, because I said, how could you get these numbers? I never could figure it out. You have part above and below, and it wanted the area between them, so you had to do it in 2 pieces. Yeah, because that's a straight line. This one is slope of 3, offset by 1. And so that's what messed you up on that one. And I got scratches all over the page because I was trying to figure out what went wrong. couldn't tell for sure. Yeah, I think that's for sure. E to the sine of phi halves is 1, just e to the 1 minus the sine of 0 is 0, e to the 0 is 1. And I didn't know how you got this, but it doesn't come out. E is 2.7 minus 1 is 1.7 or so. Yeah, so your whole problem is set up to work properly except the evaluation of it. And kind of the same thing here too. I was sort of having some trouble following it. But the 2/3 got left off. It's the only thing I can tell. Because when you integrate this, you get to the 3/2. You can't tell the 2/3 there. Otherwise, it looked like it was fine. But then 2, sine of phi halves is 1, sine of 0 is 0. So that would have been 2/3. That was the answer was 2/3. So what do we even calculate? Oh, maybe. See, everything you did here was right, except I couldn't see where you ever integrated this. It looked like you just went down here. I mean, I don't know. And here it was just a sign. That's not so easy to miss. So yeah, everything you did, it looked like you were right on the money. Now this one looked like I couldn't tell, I couldn't make out all the scratch, but I thought, you put enough effort in, I'll get enough credit for it.
Yeah, I tried it a couple times.
Yeah. But